Hi guys, my name is Luke Bennick and I'm here with 3Helix, and in this short video I just wanted to talk to you about how you can use collagen hybridizing peptides to visualize collagen remodeling within the skeletal tissues. Now this could be helpful for skeletal diseases or even monitoring bone development. So before we get started, I want to talk to you guys about the background involving collagen. So collagen fibers are based on a hierarchical organization where the collagen fibers are built up of the collagen fibrils, and these are built up by the collagen molecules. Now the collagen molecule is in a triple helical structure where you have these individual alpha chains coming together and forming this triple helix. This can be thought of the same way as rope is made out of separate pieces of twine, and you get three pieces of rope together and it makes it a lot stronger when it's together. So in this example, you have this nice intact piece of collagen, and it's a nice triple helical formation. However, it can be unfolded and start to unwind if it gets damaged due to collagen remodeling, mechanical overloading, chemical denaturation, or even enzymatic action. So what we did is we developed a collagen hybridizing peptide. So if you want, imagine this as a collagen fiber, and we have a certain amount of enzymes that can act on the collagen triple helix. These are known as matrix metalloproteinases, or MMPs. So they will cleave the collagen into separate individual strands, and what happens is now you have all these single-stranded collagen molecules exposed to the microenvironment. Our collagen hybridizing peptide is a short repeating sequence containing a glycine, proline, and hydroxyproline residue, and this small peptide can actually hybridize with these denatured collagen strands and reform the collagen triple helix. So what we have done is we've been able to put fluorescent tags on our CHPs, and then they will readily hybridize and reform that collagen triple helix with the damaged collagen strands. So going back to the first example, we have a nice intact collagen triple helix. It then becomes damaged, and the collagen triple helix begins to unwind. Now our short peptide sequence with a fluorescent probe on it can then sneak in and reform the collagen triple helix and bind to that area, indicating where there was damage or collagen remodeling. You could think of this the same way as a DNA primer binding to DNA during the PCR reaction or PCR chain reaction. So what we wanted to do with our CHPs is we wanted to look at collagen staining within tissue samples. And one really good application we found is looking at bone remodeling. So in this example, we have a mouse embryo, 18-day-old mouse embryo. And in the left sample, we just stained it with our biotin CHP. And what you see is you can see the spines, you can see the ribs, and some of these digits and joints. And when we compared it with the common anti-collagen 1 antibody seen here in blue, you see that the collagen 1 antibody is universal and it stains the whole slide. This is because it's staining for intact collagen. Now, when you have the overlay, you can see that these regions where the biotin CHP are actually regions where there's higher than normal collagen turnover. And this is actually a process called endochondral ossification, where you have the soft tissues within embryos begin to form and mineralize into solid bone. And when we take it a step further, we can actually look at a time course of bone development in a mouse embryo. So starting on day 12 and moving up to day 17, and that last slide showed embryo on day 18. And you can see right around day 14, it's hard to see in the slide, but you start to see a little bit of CHP signal on where this soft tissue begins to form into solid bone. And at day 17, it's very obvious where there's still areas of controlled bone development. So this is an example of collagen hybridizing peptides targeting remodeled collagen that is in a highly controlled manner. So this is very much required for bone development and embryogenesis. The next example is going to be an in vivo example, and that's going to be focusing on a multiple myeloma disease model. First, I just want to give you some background with this new in vivo probe. We used a scrambled CHP, which cannot target damaged collagen, and then we compared it with our in vivo probe. And as you can see, this CHP can target areas of high collagen turnover, and many times this is found in the skeletal system. So you see high signal in the spine and in the joints. When you take an ex vivo examination, again, you see high signal intensity in the spine and in the joints, with almost no signal seen in major organs. Now, When we take a look at this next slide, this is a disease model containing a multiple myeloma, and we'll walk through this figure together. In panel A, you see a micro CT image of a normal healthy mouse versus the spine of a multiple myeloma mouse. As you can see, there's a lot more bone lesions due to the cancer cells eating away and damaging collagen in the spine. In panel B, this is a bioluminescence image showing that where the cancer cells are actually localizing. So the higher the intensity means there's a higher amount of cancer cells. In figure C is our in vivo CHP probe that we injected into the mouse, and you can see in the multiple myeloma mouse model you see high signal intensity in the spine, which corresponds to the high signal intensity seen from bioluminescence showing where the cancer cells are. And in fact, you see a high correlation, or the multiple myeloma mouse has a high correlation with high signal intensity compared to the normal healthy mouse. And then these last images depict collagen hybridizing peptides locating in the joints and again in the spine. We are actually currently in the process of commercializing this in vivo probe for you guys. Hopefully it'll be out in early 2020. If you want more information about this in vivo experiment, look at our biomaterials paper that was published in 2018. So in conclusion, CHPs were able to visualize collagen remodeling due to organ development. Again, this is a very controlled manner. CHPs can also be used as an in vivo probe for skeletal remodeling in a cancer model. And the CHPs were able to localize some bone lesions that developed in multiple myeloma. So again, my name is Luke Bennick. So if you have any technical questions, please feel free to contact me. The other members of my team that you might be in contact with will be Helen Kang, who's in charge of shipping and ordering CHPs for you, and then Mike Kirkness, who's in charge of our business development. And we're always looking for new applications and new partnerships. So if you have any great ideas, please feel free to contact us. Thank you.